Ladies and gentlemen, please be quiet and seated. We just solved one of the mystery things in Python, which is the self. Now we know decorator is another amazing thing in Python. And even the most experienced user in Python probably not be able to solve all the things in decorators. Today, Katie will lead us a journey to demystify decorators. Let's welcome her.
Hi, I'm Katie. Thank you for coming out today in the midst of the fire alarm crisis of 2017. That was exciting. I heard Tom just rolled right through because he's great. Presumably you're here to listen to my decorator talk. If not, I would encourage you to stay anyway because it should be fun. I hear Brandon's coming after me. So this is clearly the best room in the convention center right now. I'm not going to be taking questions up here. So if you have questions you want to ask me, I'm going to leave my Twitter handle on the lower right corner of every slide. Feel free to tweet at me. Feel free to stop me in the hall after. And yeah, thanks for coming. So I decided about 2 years ago that I wanted to give this talk. And I wanted to give this talk because for a long time, decorators just seemed like magic to me. I could use them, I could write them, but writing them mostly felt like performing a series of steps in a spell instead of building something where I knew how it worked. So that's the context of this talk. I want to take you from a place where you know what decorators do and what they're for, but not necessarily how they work, to being able to explain to someone else how decorators work and how they might write one. So we're going to get there in a few steps. First of all, I have read a lot about magic in my time, as perhaps my shirt will tell you. And one thing about magic is that you need to know true names. So we're going to start off by formally defining a decorator. And after that, we're going to deduce one way a decorator can be structured. There's going to be some loose ends to tie up in regard to how that structure actually works. And after that, I'm going to go through some common tricks and gotchas surrounding decorators. I have said that word a lot in the past 3 days. Okay, so when I'm trying to define something, I like to start by thinking of examples. And as someone who makes a living writing production code for a large app, the first example that sprung to my mind of a useful decorator is a timer. There's a lot of timing decorators, and the idea behind them all is that you want your code to run as normal, but we also want to know how long the code takes to run. So what all of the timing decorators do is they run the original code, plus they log somewhere, in this case to standard out, how long that code took to run. If you were here for Tom's talk, you may have heard about the class method decorator. It's another common one, and it's been a built-in Python for a very long time. And what it does is it allows a method that's been defined on a class to be called without instantiating an instance of that class. Super useful. And so what both of these examples do is they add behavior to an object. Both of these cases, the object with behavior being added to it is a function, without changing the source code of the functions themselves. Ta-da! Just to reiterate, decorators change the behavior of an object without modifying the source code. Decorators are sometimes called wrappers, and as these names perhaps illuminate, the concept here is that the added behavior, whatever it may be, is by and large separate from and wrapped around the modified object, whatever that may be. So most function decorators can be applicable to arbitrary functions because function decorators shouldn't depend on what they wrap. That is, it can be reused. So let's just really hammer home the benefits of using a decorator to add extra behaviors to functions. So imagine that you have a function that you'd like to time. Maybe you notice that it seems to perform much better with some inputs than others. And what you want to be able to do is to run your functions with different inputs and say log to standard out the time spent in that function. So there are two different ways that I can think of doing this. And one way is to just add code to my function itself. So you could import time, get the time before anything happens in the function, keep the original body of the function, get the end time. The time spent in that original body is going to be the difference between those times, so you print those to standard out, and then you return the original return value. Do this every time you run my function, you'll print to standard out how long the original body takes to execute. Does what you want, right? Alternatively, you could use a timer decorator. And I'm not going to show you the source code for my timer yet. It's just a mystery for now. But it does the same thing as adding timing and printing lines to the source code of my function. It does also have the convenient benefit of making it really explicit that the timing behavior is extra. It's not inherent to whatever my function is doing. And more importantly, the timing decorator can be reused to time additional functions, which is not a thing that I could have done with the constructed timer on the last side. I would have had to cut and paste those lines of code into a bunch of other functions. That's annoying. So in order to gain intuition for how a decorator works, we first need to make some explicit statements about the objects that decorators are frequently applied to. So technically, decorators in Python can be applied to either functions or classes. More on that later, but stick with functions for now. And very simply, in Python, functions are first-class objects. And first-class objects are entities that they can be assigned to variables. First-class objects can be passed to functions. First-class objects can be returned from functions. And first-class objects can be dynamically created within functions. So the upshot of all of this is that, well, hang on. The first upshot is that I can refactor that really, really terrible constructed timer code I wrote a couple slides ago. I got like 23 minutes left. That code is really bad, so just we're gonna take a minute to fix it. So specifically, what really bothers me about the technique of adding extra functionality to a function by just sticking lines of code in there is twofold. First of all, that extra timing code distracts you from the function code. There's a bug in there. Now there's like triple the lines of code that I have to parse, right? Secondly, the extra timing code will need to be copy-pasted to be used anywhere else, as I've alluded to before. And so the refactor that I want to do right now, given that functions are first-class objects that can be passed into other functions, a first step towards improving the constructed timer is to make a new function that gets passed the original function and its argument, like so. I'm going to call this a timing wrapper. And so timing wrapper gets the start time, runs the function argument it's passed with, runs the function it is passed with the argument that is also passed to it, gets the end time, prints the difference between those times, and returns the value that the function it was passed returns. And so I can use this to time any function that takes one argument. All I have to do is just call timing wrapper with both the function I want to time and the argument I want to run that function with. So it satisfies my goal of making the timing code usable on more than one function, because I can pass in any one argument function there. But it's also worse than the original code. I'm not happy right now. Each call to a timable function has to explicitly be wrapped with timing wrapper, because this code is effectively adding the timing code at runtime. It's not timing until you want to call the function. So in a large code base, if you have many, many, many calls to my function, it's going to be really annoying to have to search for every single call to my function and replace it with a call to timing wrapper instead. Terrible. So that means that there's really an extra refactoring goal that was hitherto implicit. So what I really want to do is I still want to be able to time arbitrary functions. I still want to combine that feature of timing wrapper of being able to be used on any one argument function. But I also want to preserve the feature of the original code, which was that the timing functionality is baked in at definition time for that function. So I added those lines to my function, and then every single call to my function had the timing code. That was great. I want that. So these first two refactoring goals, just to reiterate, I did that by wrapping the function that I wanted to time in another function that adds the timing code and has a callback to the original function. And the third goal of having this functionality baked in at definition time, that was achieved simply by including the timing code in the source code for the timed function. So these two goals seem irreconcilable. At this point, I have 19 minutes left. Maybe I should just give up. But wait. Functions are first-class objects, so we can create them dynamically within another function, and we can also return them from functions. That's great. So that means that I can dynamically create a new function that has timing code in it, as well as a callback to the original function, whatever it may be. And that's a big step, perhaps a big leap. So I'm going to repeat it. The refactor that I really want to do is to make a function that takes an arbitrary function, and then inside this function, which I've called my timer, I'm going to create a new function that includes both timing code in its source as well as a callback to the original function. And then I'm going to return that new function that I've created in my timer. And again, all of this I can do because functions are first-class objects. So if I want to create a timed version of my function, the way I would do that is I would call my timer with my function as an argument. That'll give me a new function. Here I've named it timed function. And that function does everything my function does and also is timed. So in terms of what that would actually look like, I'm essentially going to put the timing wrapper intermediate step inside a function that takes a single argument. And that single argument is the function to be timed. The return value of my timer is this new wrapped function, and that's actually what will get called in our code. What new wrapped function is it gets the start time, it executes func with an argument, it gets the end time, it logs that to standard out, and then it returns the value that func would return. At this point, you're probably wondering how we have access to the name func inside of new wrapped function. That's a great question. I'm going to utterly ignore it for now. And one last thing. Functions are first-class objects, so we can assign that return value to whatever we want. On the previous slide, I called it timed function, but we may as well assign the returned function to the name of the function that we want to time and just replace it. If we do this, then after that line in which we replace foo, every single call to foo will have timing. So I won't have to search the entire code base and replace a bunch of calls with a new name. And this is the state in which I'm gonna leave this. It's my final step in refactoring. As it is, I can use this myTimer function to add timing functionality to any one argument function immediately after that function is defined, which fulfills all of my refactoring goals. That's great. I'm super happy. So happy I'm going to take a drink of water. But now I have about 15 minutes left, so now we should really get back to decorators. Thank you for going on that tangent with me. But wait, replacing a function with the return value of a function called with the original function as an argument is in fact decorating that function. And up until Python 2.4, that was how you decorated anything. This is from the PEP that proposed adding syntactic sugar for decorators. And this is an example of how prior to Python 2.4, you would decorate a method as with the class method decorator. You would define foo, and then on a new line, you would replace foo with the result of class method called with foo. And that's clunkier than is really necessary. So there was a PEP to fix that, and you may have guessed that the syntactic sugar decided on in PEP 3.18 was in fact that decorating function like this is going to be replaced with the @ sign followed by the name of the decorator on the line above the function definition. So just to reiterate, the @ decorator syntax, when used to decorate a function, is just syntactic sugar for replacing that function with the return value of a callable object called with a decorated function as an argument. That's it. So I can also come up with a more nuts and bolts definition of a Python decorator, namely that it's a callable object that takes a function as an argument and replaces the decorated object with the decorator's output when called with the following decorated object, which changes the behavior of that object for all future calls to that object. Great. In terms of how we'd actually write such a thing, well, as you may have guessed from all of that refactoring, a common decorator anatomy looks a bit like this. So working from the outside in, our decorator is going to be a function which will be called with a function as an argument. So it takes a single argument, which I've called func just to hammer home that it's a function. If you're trying to write a useful decorator, it will probably create a new function and probably return that function, which is going to replace the function that it decorates. And in terms of what this new function looks like, because it's going to replace the decorated function, it needs to have the same signature as func. So a common way of ensuring that is just to splat the arguments to the new function. So that's what I've done here. And then inside new function, well, the most common reason for writing a decorator is to extend the behavior of a function, not to replace it. So probably what the wrapper function is going to do is probably call func, probably return the return value of func, as well as probably containing some new code. Seems reasonable. So I use the word probably a lot on that last slide because there's really quite a lot of leeway in terms of what decorators can do. So the only requirement for the code to compile is that the decorator takes a single argument. I don't actually have to define anything new in the decorator. I could, for example, decorate a function with this no-op decorator, which just takes the function, returns the same function, so it wouldn't change the thing that it decorates. Seems mostly useless, but I could do it. I tested it in a REPL. It works. A decorator doesn't have to actually call the function that it decorates. So I could use sleight of hand to just replace whatever I decorate with something that always returns 42. Don't know why I'd want to do that, but I could. And finally, a decorator doesn't actually have to return a function in order to compile. So in theory, I could decorate something with this black hole that just returns none. The code will compile. If I were to say decorate something called foo with black hole, yeah, I'd have a foo object. If I try and actually call foo, I'll get a type error because none isn't callable, and that'll be real confusing, but I could do it. So none of these are particularly helpful, none of these are particularly useful, unless your main goal is having bad ideas, which is a good goal to have. But they are all legal decorators according to Python's grammar. You could use all of these functions to decorate something else. Work fine. By some definition of fine. So now we're done, right? At this point, we've worked through what the syntactic sugar is like actually doing. We've worked through one way of structuring a decorator that is useful. We've even seen how you could write totally useless decorators. But we're not actually done. So I still haven't explained how the inner function that's created inside of a decorator has access to the function that's passed in as an argument to the decorator itself. I haven't explained a lot of things. So here are some more open questions that I can think of off the top of my head, by which I mean when I prepared this talk. So what is that @wraps decorator that makes appearances in decorator examples? Like, so many people use @wraps, why? If you have a function that's decorated multiple times, what order are the decorators resolved in? That's kind of important in a couple examples that I can think of. And how does the syntactic sugar actually work? All of these are excellent questions. I will answer most of them. Let's start with how the wrapper function accesses the function that it's going to replace. So when functions are created in Python, they create a new scope or namespace for themselves. And namespaces store references that are accessible for that function. So here, for example, we know that we can access some arg inside of my function. Printing it works. So if I were to print the local scope of my function by using the built-in locals, some arg is going to appear there. It's going to say, hey, inside of my function, some arg is 1. So going a step further, in Python, it so happens that a function's scope includes the scopes of functions enclosing it. So if we write a function within a function, who knows why we would ever do that, such as here, some arg is actually still accessible from within inner function because it's present in my function's scope. And there's a lot more that we could talk about in regards to scope, but in terms of decorators, this is really all we need to know. Because the scope of an enclosing function is accessible from the function it encloses, if some arg was in fact a function that you passed into my function, I could call it from within the inner function. That'd be fine. So now we've talked a lot about how good decorators are. They let you wrap functions with extra behavior. They're reusable. They're fun. You can use them for bad ideas, et cetera, et cetera, et cetera. They're great. And now it's time to actually discuss a problem that they cause and how we can use another decorator to mitigate that problem. So looking back in the implementation of my timer, we can see that the name of the function that we're going to replace func with is new wrapped function. So that means that if we were to decorate a function with my timer and then use the dunder name attribute to get the name of that function, we'd get new wrapped function instead of foo, which is what at least I would expect to see if I were to access the dunder name attribute on foo. And that's because what's actually happening here is the name foo points to a function whose name is new wrapped function. This misdirection is, I think we can all agree that this is not great. Sometimes people write programs that rely on knowing function names. For using my timer to decorate many functions, then you're going to have like exponential things whose name are new wrapped functions. It's bad. So functools solves this. The wraps decorator from the functools module mitigates that problem by, first of all, replacing the wrapper's name with the name of the function it's decorating, replacing the wrapper's docstring with the docstring of the function it's replacing, and it's applied to the wrapper as, you guessed it, a decorator. And that's why you have probably, or at least hopefully, frequently seen decorators that are written like this, with the inner function decorated with the wraps decorator. I'm going to leave implementing that decorator as an exercise for you. So another common point of confusion is what order decorators are applied in when a function is decorated multiple times, which is a thing that I haven't even mentioned yet. Functions can be decorated multiple times. Like here. So my timer is a decorator that executes a function and then prints how long the function took to run. And another decorator is another decorator that does something else. And there are situations in which the order these decorators are applied might matter to you. Like maybe you know that whatever is happening in another decorator takes a really long time, and you don't care about timing it, you only want to time foo. So you want to make sure that another decorator is applied after my timer. Have you done it right? Well, remembering that a decorator replaces what follows it with the result of the decorator called with the function following it, our question is really, does my timer replace foo and then in turn get replaced by another decorator, or does another decorator replace foo and then get replaced by my timer? And the rule of the @sugar is that it replaces what immediately follows it. So since my timer is on the line immediately above the definition of foo, my timer replaces foo first, and then another decorator is called on the result of my timer called with foo. And this actually makes me very happy because I came from math and science background, and like that, this looks normal. This looks normal to wrap this way. Also, I like to think of stack decorators as layers of an onion. So each decorator is going to wrap what comes below it, and the higher in the stack you go, the more it's going to wrap. There are so many more questions that we could answer about decorators, but I am running kind of low on time. So I've told you what the @syntactic sugar is doing, but not at all how it works. That requires learning at a kind of high level the steps taken to turn Python code into executable machine instructions. Some decorators take arguments. None of the ones that I have shown you in this talk do. I'm not going to show you how that works. Sorry. I've only addressed decorators that decorate functions. But since Python 2.4, decorators have been able to be applied to classes as well. Haven't shown you how that works. I've also only shown decorators that are functions, but really what the syntactic sugar is doing is just calling the decorator. So you could write a decorator as a class that has a dunder call method, and that would work just fine. And finally, I'm not going to implement @wraps right now at PyCon in front of so many people. Not happening. And I don't really feel too bad about skipping any of this, because these are all questions that you can hopefully answer for yourself, armed with the knowledge that you have now in terms of how decorators work. So next time somebody asks you this question, just remember, all the Python decorators do is replace whatever they decorate with the return value of the decorator called with that object, and that's it. No other rules. So these are some blog posts that I found helpful when I was trying to frame how to run this explanation. Also, there's a link to the PEP that is pretty cool, pretty fun read. And that's basically all I got. So thank you for coming. Thank you for braving the fire alarm. Thank you to everyone who proofread this and told me not to talk about parsers and compilers. Very helpful feedback. Thank you. And I wanted to give this talk because for a long time, decorators just seemed like magic to me. I could use them, I could write them, but writing them mostly felt like performing a series of steps in a spell instead of like building something where I knew how it worked. So that's the context of this talk. I want to take you from a place where you know what decorators do and what they're for, but not necessarily how they work, to being able to explain to someone else how decorators work and how they might write one. So we're going to get there in a few steps. First of all, I have read a lot about magic in my time, as perhaps my shirt will tell you. And one thing about magic is that you need to know true names. So we're going to start off by formally defining a decorator. And after that, we're going to deduce one. Hi, I'm Katie. Thank you for coming out today in the midst of the fire alarm crisis of 2017. It was exciting. I heard Tom just like rolled right through because he's great. Presumably you're here to listen to my decorator talk. If not, I would encourage you to stay anyway, because it should be fun. I hear Brandon's coming after me. So this is clearly like the best room in the convention center right now. I'm not going to be taking questions up here. So if you have questions you want to ask me, I'm going to leave my Twitter handle on the lower right corner of every slide. Feel free to tweet at me. Feel free to stop me in the hall after. And yeah, thanks for coming. So I decided about 2 years ago that I wanted to give this talk. That code took to run. If you were here for Tom's talk, you may have heard about the class method decorator. It's another common one, and it's been a built-in in Python for a very long time. And what it does is it allows a method that's been defined on a class to be called without instantiating an instance of that class. Super useful. And so what both of these examples do is they add behavior to an object. Both of these cases, the object with behavior being added to it is a function, without changing the source code of the functions themselves. Ta-da! Just to reiterate, decorators change the behavior of an object without modifying the source code. Decorators are sometimes called wrappers, and as these names perhaps illuminate, the concept here is that the added behavior, whatever it may be, is by and large separate from and wrapped around the modifier.
Ladies and gentlemen, please be quiet and seated. We just solved one of the mystery things in Python, which is the self. Now we know decorator is another amazing thing in Python. And even the most experienced user in Python probably not be able to solve all the things in decorators. Today, Katie will lead us a journey to demystify decorators. Let's welcome her.
The way a decorator can be structured. There's going to be some loose ends to tie up in regard to how that structure actually works. And after that, I'm going to go through some common tricks and gotchas surrounding decorators. I have said that word a lot in the past 3 days. Okay, so when I'm trying to define something, I like to start by thinking of examples. And as someone who makes a living writing production code for a large app, the first example that sprung to my mind of a useful decorator is a timer. There's a lot of timing decorators, and the idea behind them all is that you want your code to run as normal, but we also want to know how long the code takes to run. So what all of the timing decorators do is they run the original code, plus they log somewhere, in this case to standard out, how long